Hello and welcome back to Mysterious Science. My name is Paige and today we've been asked by Megan to explain why her soda can keeps exploding in her car when it's hot out. Here at Mysterious Science, we've decided the best way to show this is to perform an experiment simulating Megan's situation. You know how we love making things explode. So, Megan put a typical soda can into her hot car, like so, and goes to school, and when she comes back, her soda can has exploded. Let's go to Josh, our lead scientist, and see an accurate simulation of what happened.
Now presenting a soda can implosion, which is a slightly varied experiment of what happened to Megan's soda can. Since exploding a soda can was too dangerous to do in our lab, we decided to do the opposite and implode the can.
Thanks for that, Josh. Now it's time to solve this mystery. Are you ready, guys? I'm here in the studio with our historian, Tatiana, and she's going to tell us exactly how this happens. So, Tatiana, how does this happen?
Well, Paige, science follows a specific set of rules. No matter what is happening around you, you can always find a rule to explain it. The rule to explain Megan's soda can scenario is Gay-Lussac's law, which describes the behavior of gases.
What exactly is Gay-Lussac's law?
Alright. Gay-Lussac's law is the relationship between temperature and pressure. The temperature and pressure of an ideal gas are directly proportional as long as its volume and mass remain constant.
Wow, Tatiana, that's a little bit confusing. So, for our viewers, can you explain that in a little bit easier terms for us?
Absolutely. Why don't I give you an example? If we have a volume of container and the volume is held constant, constant meaning it doesn't change, and then we have X amount of gas inside the container, Gay-Lussac's law dictates that as the temperature of a gas increases, the pressure inside the container will also increase. There's also even a cool equation to go along with the law, but for that we'll need to turn this discussion over to Olivia.
Hello and welcome back to Old Dead White Guys of Science.
Today we're going to be learning about Louis Gay-Lussac, also known as this guy right here. During his first major research program, Mr. Lussac concluded that the equal volumes of all gases expanded equally with the same increase in temperature. So, volume A, filled with X amount of gas, and volume B, filled with the same amount of gas, would equally expand and gain temperature at the same rate. This conclusion is usually called Charles's Law in honor of Jack Charles, who had arrived at nearly the same conclusion 15 years earlier, but had not published it. 1804 is when Mr. Gay-Lussac gathered information to back up his theory and investigated other gases. How did he do this, you ask? Well, he did this in a very daring way. Mr. Lussac made several ascents of over 7,000 meters above sea level in a hydrogen-filled balloon, a feat not equaled for another 50 years. This allowed him to investigate other aspects of gases. Not only did he gather magnetic measurements at various altitudes, but he also took pressure, temperature, and humidity measurements and samples of air, which he later analyzed chemically. Finally, 1808, the year that Gay-Lussac announced what was probably his single greatest achievement. From his own and others' experiments, he deduced that gases at constant temperature and pressure combine in simple numerical proportions by volume, and the resulting product, or products if gases, also bear a simple proportion by volume to the volume of the reactants. So basically, if the volume of a container is held constant as the temperature of a gas increases, the pressure inside the container will also increase.
Alright, now let's head over to Olivia. Olivia, how are you today?
I'm good, Paige, thank you.
What do you have for us today?
Today we're going to be going over the formula for Gay-Lussac's law, and if we have time, we'll do a few practice problems.
Sounds great. Olivia, take it away.
So here is the question for our first example. We're going to try to determine the pressure change when the gas is heated. So we must remember that our equation is the first pressure over the first temperature is equal to the second pressure over the second temperature. And we also have to remember to convert to Kelvin when we're dealing with our temperatures. And to convert to Kelvin, it is Kelvin is equal to degrees Celsius plus 273. So if we take our equation and then input our variables, so our first pressure is 1 atm in the bouncy house, and our first temperature is 20 degrees Celsius is equal to our second pressure over the 30 degrees Celsius, but we're still trying to find the second pressure. Now once we convert to Kelvin, it is equal to 1 atm over 293 Kelvin is equal to P2 over 303 Kelvin. And then to solve that, we cross multiply. So it would be 130 times 293 P2. And if we continue to simplify, we find that the final pressure is 0.102 atm in the bouncy house. So here's example 2, the one with the dentist. So now we have to remember this formula, P1 over T1 equals P2 over T2. So we have our work here, we're substituting, so we have 6 atm over 27 degrees Celsius is equal to P2, our variable, over 77 degrees Celsius. Now, we have to remember to change this to Kelvin. So 27 degrees Celsius is 300 in Kelvin, and 77 degrees Celsius is 350 Kelvin. Now, what we want to do is we're going to have to cross multiply. So it would be 6 atm times 350 atm, and P2, our variable, times 300 Kelvin. When you simplify that out on either side of the equation, we're going to have 2,100 is equal to 300, our variable. When you simplify that down, by dividing both sides by 300, you get 7 is equal to P2. And from that, we learn that the pressure is now 7 atm in the laughing gas. And here's example 3, the one about the car. Remember our formula. In this time, since we aren't talking about temperature, since the temperature in the garage was constant, we don't have to change anything to Kelvin. So here's substitution in the formula. So we have our initial pressure with our initial volume, and then our secondary pressure, which is our variable, and our secondary volume. Now we cross multiply, so it becomes 446 times 12 and 8.25 times the second pressure. So once we solve it out, it is 5,352 is equal to 8.25 times the secondary pressure. And when you divide this side by 8.25, you get 648.72 is your secondary pressure.
That's all the time we have for today, guys, but we'll see you next week on Mystery Science. And remember, safe science is awesome science. Send us your science questions and we just might pick up your story.